Welcome back to The Explainer. So glad you're here. Today, we're pulling back the curtain on a seriously crucial yet kind of invisible piece of tech that literally powers the internet. Have you ever stopped to wonder why your favorite streaming service or, a massive e-commerce site doesn't just instantly crumble to dust when millions of us log on at the exact same time? Well, the secret sauce keeping our digital world running smoothly under all that pressure, it's not magic. It's a brilliant piece of architecture. Today, we are demystifying the load balancer. Let's get into it.
Okay, let's dive into this. Here is our roadmap for today. First, the single server nightmare. Second, enter the load balancer. Third, we'll look at smart traffic routing algorithms. Fourth, layer 4 versus layer 7. And finally, managed cloud solutions.
All right, section 1, the single server nightmare, when traffic spikes strike.
So the stakes are incredibly high here. And honestly, this is the foundational nightmare every system architect is trying to avoid. You build an incredible app, it goes viral, and boom, suddenly millions of users are rushing in. But if all those requests are pointing at just one single server, it's game over. Literally. A server has finite resources, right? CPU, memory, network bandwidth. When the volume of incoming requests completely blows past what that hardware can actually process, the server overloads. It slows to an absolute crawl, drops connections, and eventually, well, it figuratively catches fire and crashes. Your app goes offline exactly when it's the most popular. Absolute nightmare.
Which brings us to section 2. Enter the load balancer, the ultimate traffic cop.
Obviously, we can't just let our servers burn to the ground. Look at the stark contrast here. On the left, we've got that nightmare scenario. One server taking the entire brunt of the traffic and inevitably crashing. But on the right, we introduce our hero, the load balancer. By placing this piece of tech in front of a pool of servers, that exact same massive crowd of users is effortlessly managed. The traffic gets distributed evenly across 3 separate servers. No single machine gets overwhelmed, and the whole system achieves high availability. This immediately answers why this technology is an absolute, non-negotiable must-have for scaling any application. So what is it exactly? To put a formal definition to it, a load balancer is essentially a smart reverse proxy. It sits directly between your end users and your backend servers. Its one and only job is to seamlessly and intelligently distribute incoming network or application traffic across a whole cluster of servers. And this brilliantly illustrates that exact positioning. Notice how the user doesn't even know there are multiple servers in the background. They just don't see it. The user simply connects to the load balancer, and then the load balancer acts as this highly efficient middleman. It intercepts the request and dynamically directs it to an available, healthy server in the backend pool. It creates this totally seamless illusion for the user, all while doing some incredibly heavy lifting behind the scenes. By sitting in that crucial middle spot, load balancers unlock 4 massive superpowers for your infrastructure. First up, high availability. If one server goes down, the traffic just naturally routes to the healthy ones. Second, better performance, mostly because requests are handled by the least burdened machines. Third is easy scalability. You can just seamlessly add more servers to the pool as you grow. And fourth, enhanced security, since it actually acts as a protective shield against certain types of cyber attacks. Taking a closer look at these benefits visually, that bright blue shield locked onto the server stock really perfectly captures the essence of what we're talking about here. The load balancer isn't just a traffic director. It's a completely critical layer of defense. It masks your internal server infrastructure from the public internet. And by balancing that load, it guarantees that your application remains highly available and super performant, literally no matter what the internet throws at it. Okay, section 3, smart traffic routing algorithms, the playbook. So how does it actually choose which server gets the traffic? It's a fantastic question to ask yourself right now. Out of a pool of 5, 10, or even 100 servers, how does the load balancer know exactly which one gets the very next request? Well, it's definitely not random. There's a precise, highly logical toolkit of algorithms at play. Let's actually look at them one by one. Now, what's really interesting about this slide is how beautifully simple this first algorithm is. It's called round robin. You can think of it kind of like dealing a deck of cards. Request 1 goes to server A, request 2 goes to server B, request 3 to server C, and then, for request 4, it loops right back around to server A. It's sequential, it's perfectly fair, and if you're dealing with servers that have identical hardware and similar tasks, it is incredibly effective. But what happens if some requests take way longer to process than others? That is where least connections comes in. This is a much smarter distribution method. The load balancer actively monitors the backend in real time. It sees, okay, the top server has 2 active connections, the bottom has 4, but hey, the middle one only has 1. So it intelligently routes the brand new incoming traffic straight to that middle server, putting that underworked, frankly, kind of lazy machine back to work. It actively avoids creating bottlenecks by finding the machine with the lightest current workload. Next up, we have IP hash. Now, this one is absolutely crucial for applications where a user needs to stay logged into a specific session. Notice how the user with the IP address ending in .10 always gets routed to the top server, and the user ending in .11 always goes to the bottom server? By mathematically hashing the client's IP address, the load balancer guarantees that a specific user is permanently sticky to a specific server. This ensures a perfectly consistent, uninterrupted experience for things like, say, digital shopping carts or complex login sessions. Then we've got the weighted algorithm. Let's face it, not all hardware is created equal, right? Sometimes you have a brand new, super powerful server sitting right next to an older, much slower one. By assigning weights, you can tell the load balancer to intentionally give that top server, let's say with a weight of 5 times as much traffic as the bottom server with a weight of 1. It basically allows your infrastructure's most powerful machines to intentionally do the heavy lifting. It optimizes your exact hardware setup.
Finally, we have my personal favorite algorithm, least response time. This one is incredibly dynamic. It actually combines the number of active connections with the real-time speed of the server's response. Look at the metrics here: 120 milliseconds, 50 milliseconds, and 200 milliseconds. The load balancer is actively testing these speeds, and it immediately routes the next batch of users straight to that 50 millisecond server. It is constantly adapting on the fly to ensure the fastest possible performance for the end user. Real game changer. Moving on to Section 4, Layer 4 versus Layer 7, Express Lane versus Smart Lane. You can think of this as the difference between a high-speed post office sorting facility and a dedicated personal assistant. Layer 4 is the express lane. It only looks at the outside envelope, the IP address and TCP port. It doesn't care at all what's inside the message. It just forwards it at absolute lightning speed. Layer 7, on the other hand, is the smart lane. It actually opens the envelope. It reads the HTTP request. It looks at the URLs, inspects the cookies, and makes highly intelligent routing decisions based on the actual content of the user's message. Yes, it requires a tiny bit more processing power, but the granular control you get is just incredible.
So, the crucial point here is how you apply this networking knowledge. As we break this down, if you are building a system where raw, uncompromising speed and huge volume are literally the only things that matter, the Layer 4 transport layer is absolutely your express lane. But if you need to route mobile users to one specific server cluster and desktop users to another, or maybe route video traffic differently than text, then you absolutely need the application-level intelligence of Layer 7.
And finally, Section 5, Managed Cloud Solutions, the modern approach.
Let's move to the real world and see how this builds out today. Because the truth is, most modern development teams just aren't racking their own physical hardware to do this anymore. Today, the industry standard is relying on managed cloud services. Major players like AWS with their Elastic Load Balancer, Google Cloud Load Balancing, and Azure Load Balancer have totally transformed this technology from a hardware headache into a simple, scalable software service. You really don't have to worry about maintaining the underlying infrastructure anymore. These cloud giants handle the reliability, the scaling, the whole shebang, including failovers, all for you with just a few clicks in a dashboard. So, after exploring the single server nightmare, all those brilliant algorithms, and modern cloud deployments, I want to leave you with this final critical question. Is your app one traffic spike away from a crash? Understanding load balancers isn't just about dry networking theory. It's about guaranteeing your project actually survives its own success. I really hope this explainer gave you the clarity to go out there and architect systems that are truly uncrashable. Thanks so much for joining me, and we'll catch you in the next one.